You're not behind, you're playing the wrong game. Because quantum mechanics isn't hard because you're not smart enough. It's hard because your brain was trained on the wrong operating system, everyday reality. Let me prove it in 10 seconds. Right now, look at your hand. Your brain says, solid, certain. Here, quantum mechanics says, mostly empty space with invisible rules that behave like probabilities until you check.
Right.
And if that makes you slightly uncomfortable, good. That discomfort is the doorway. So that right there is the mission today. We are taking what is, I think, maybe the most intimidating gatekept topic in all of science, and we're just stripping it down to the studs. No equations, no Greek letters that, frankly, I can't pronounce. We're scrubbing the whiteboard clean.
And honestly, that's the only way to really get it. If you start with all the math, you get lost in the mechanics of it all.
Yeah.
You miss the meaning.
Right. So we're going to unpack this thing the way you'd explain a really high-stakes system in a boardroom. We're just looking for the principles, the mental models, the actual rules of the game. Because looking at this stack of research you pulled for this deep dive, the promise here is it's pretty aggressive.
It is aggressive, but it's true. Look, the goal isn't for you to walk away from this and, pass a physics exam at MIT.
Right.
It's to have you realize that quantum mechanics, it describes the limits of certainty in your own life. It actually changes how you look at decision-making, information, even who you think you are.
So it's not just trivia, it's a new operating system.
Exactly.
Okay, let's install the upgrade. To do that, I think we have to start by debugging a huge error in how most of us even see the world, this two worlds.
This is the biggest stumbling block for everyone. We have this mental map, right, where there's the normal world, basketballs, electric bills, this microphone.
My coffee cup.
Your coffee cup. And then somewhere else, maybe in a billion-dollar lab or a galaxy far, far away, there's the quantum world with all the atoms and the weird stuff.
Well, there are two different rooms in a house. You just walk out of the quantum room and you're back in the normal one.
Precisely. But that's a lie. I mean, it's a useful lie for getting through the day, but it's just wrong. There is only one world. The quantum rules are running 24/7 right here, right now.
Okay, so then why does my desk look solid? Why does my coffee cup stay where I put it if it's really just some buzzing quantum mess?
Okay, think of it like a city. Imagine you're in a plane, say, 30,000 feet up, and you're looking down at a huge city at night. What do you see?
You see a grid, glowing lines. It all looks static, organized. The traffic flows look like a smooth streams of light. Predictable.
Smooth, coherent,
Yeah.
right. But now, zoom in. I mean, drop all the way down to street level. What happens to that smoothness?
Oh, it completely shatters. You're on the sidewalk. You've got a guy running for a bus. Someone spills their coffee. A taxi cuts someone off. It's just individual decisions. Chaos. Noise.
Exactly. Quantum mechanics is just the zoomed-in version of reality. Classical physics, that world of baseballs and gravity, that's just the summary your brain writes to survive.
It's the view from the airplane.
It's the view from the airplane. But the street level, that's where the real action is.
I love that visual. So we aren't stepping into a new world. We're taking the filter off the one we're already in.
We're zooming in.
Which brings us to the first character in our story, the particle.
The particle.
Now, I gotta be honest, when I read the word particle, my brain immediately renders a tiny, tiny little marble, a microscopic ball bearing just zipping through space.
Then you have to delete that image right now. That is the source of almost all the confusion. A particle is not a marble. In quantum mechanics, what we call a particle behaves more like a wave of possibility.
A wave, but not like, a wave in the ocean.
No. Think of it as a probability cloud. It's really just a mathematical description of where the particle might be. It isn't in one specific place. It's kind of smeared out across all the places it could be.
Okay, the research you sent over uses an analogy that I think just nails this perfectly. The teenager and the dinner choice.
Oh, yeah. It sounds funny, but it maps the physics surprisingly well.
So, okay, imagine a teenager. You ask them, hey, what do you want for dinner? Now, before they actually say the words, what is the reality of dinner?
It's not fixed. It's not pizza yet.
Right. It exists as this weighted cloud of probabilities.
Exactly. In that cloud, there's maybe a 60% chance of pizza, 30% of pasta, and like a 10% chance of I'm not hungry.
Which we all know is the statistical outlier, the anomaly. But okay, here's the critical part that I want to make sure I get right. Until they speak, until that interaction happens, all those options exist at the same time. It's not like they've secretly chosen pizza and just haven't told you yet.
That is the key distinction. The choice literally hasn't happened. The teenager is in a state of potentiality. The pizza reality and the pasta reality are actually overlapping.
And the moment they say pizza,
Collapse. The cloud just vanishes. One outcome becomes real, and all the others, they just disappear. That's the essence of quantum measurement.
so before you measure, you have a menu of possibilities. After you measure,
You have a meal.
this leads to that phrase that always sounds a little mystical, maybe even a bit arrogant. The universe depends on observers.
It's not mystical, though. And it's definitely not about human ego. People hear observer and they think it has to be a human being with eyes, maybe a PhD. It doesn't.
So what is it?
In physics, an observer is just an interaction. It could be a detector, a wall, a single photon of light hitting an electron. Anything.
So reality isn't waiting for my consciousness to give it an opinion.
No.
It's just waiting for a check.
It's waiting for an interaction to force a definite outcome. The universe loves to stay in that menu phase for as long as it possibly can. It only cooks the meal when something forces it to.
And this concept, multiple states until interaction, that's what leads us to superposition.
Superposition. The idea that a system can physically be in multiple states, multiple configurations, at the exact same time.
We usually hear about Schrodinger's cat here, dead and alive, but let's skip the animal cruelty. The notes suggest we use modern anxiety. The vibrating phone.
Okay, let's do it.
Your phone buzzes in your pocket, you haven't looked at it, you have no idea who it is. So, in your mind, what is that notification?
It's an unknown. It could be anything.
But it feels like a superposition, right? It is simultaneously. A text from a friend you've been waiting to hear from, a spam call about your car's extended warranty,
A terrifying email from your boss.
or the group chat just exploding over some meme. All of those things at once.
In your mind, yeah, it occupies all those potential spaces.
And the moment you pull it out of your pocket and look,
Collapse.
yeah.
The reality settles into one single option.
Now, in everyday life, of course, that message was already determined before I looked. It was always a spam call. I just didn't know it yet.
Correct. And that's just a lack of information. We'd call that classical ignorance. But in quantum mechanics, the system literally behaves like it's all of those things at once.
So it's not that we don't know.
It's that nature hasn't decided. The particle is physically navigating multiple possibilities simultaneously.
And we know this isn't just, some stoned philosophy because of the double slit experiment.
The most famous experiment in the history of the field. This is the judge and jury of all of quantum mechanics.
So walk us through it. Paint the picture for us.
Okay, imagine a wall with two vertical slits in it, like two little doorways. And you're shooting electrons, or particles, at this wall, one by one.
Okay, so I'm firing tiny marbles at a wall with two doors. If they were marbles, they'd either go through the left door or the right door. And on the back wall, you'd expect to see two piles, a left pile and a right pile. Simple.
That's what common sense demands. That is what you would bet your life on. But that is not what happens. Instead, you get an interference pattern. You get all these bands of stripes across the back wall.
Stripes, which is what you'd get if you sent water waves through the slits. They'd ripple out, overlap, and create peaks and valleys.
Exactly. Which implies something that seems impossible.
That each individual electron, somehow,
Went through the left slit, the right slit, both slits, and neither slit, all at the same time. It interfered with itself.
that is the part that breaks the brain. One thing taking two paths simultaneously. It's like me walking through the front door and the back door of my house at the exact same moment.
It defies all logic. But then comes the twist. The part that really feels like a glitch in the simulation.
The measurement.
Right, because scientists looked at this and said, that's impossible, let's check. So they put a tiny little detector right by the slits to spy on the electron. They wanted to see which path it actually takes.
They force the teenager to choose dinner.
Exactly. And the second they do that,
Yeah.
what happens?
The interference pattern just vanishes.
Instantly. The moment you ask which slit, the electron stops acting like a wave. It snaps back to acting like marble, and you get the two piles.
It changes its behavior because we watched it.
Because we interacted with it. We forced it to choose a state.
Mm-hmm.
And this brings us to a huge mental model that I think applies to absolutely everything. Asking a question is not free.
Asking a question is not free.
Measurement is an act of interference. You cannot observe a system without altering it. You can't just check in on reality without, poking it.
That's hauntingly applicable to real life. Like, if you ask your partner, are we okay? The relationship is now in a different state than it was 5 seconds ago. You've forced a measurement.
Precisely. You collapsed the waveform of the relationship into a specific definition. Maybe it was in a superposition of okay and not okay, and by asking, You force it to resolve.
I have to pause here because this just opens up a massive can of worms. If the electron goes through both slits and only chooses one when we look, where do the other possibilities go?
That is the million-dollar question.
I mean, does the version of the electron that went through the other slit just poof, vanish?
Well, there is a school of thought, a very popular one among some physicists,
Mm-hmm.
that says no, they don't disappear. They argue those other possibilities actually happen, just not in the reality that we perceive.
You're talking about parallel realities.
I am, the many worlds interpretation. The idea that every single quantum choice spawns a branching universe. The electron went left in our world and right in another one. It's a mind-bending concept.
I'm putting a huge pin in that
Yeah.
immediately, or we will derail this entire deep dive. So, listeners, remember many worlds. We might need to circle back to that later, but right now we have to deal with another limitation reality puts on us. Uncertainty.
Heisenberg's uncertainty principle.
Yeah, the common view here is that uncertainty just means, bad data, like our ruler isn't precise enough or our glasses are smudged. If we just had better tech, we could know everything perfectly.
And that's the intuition. But Heisenberg wasn't talking about bad instruments. He discovered a built-in resolution limit of the universe. He proved that there are pairs of properties, like position and momentum, that you simply cannot define sharply at the same time.
It's a trade-off.
It's a fundamental trade-off.
Yeah.
You buy precision in one, and you pay for it with blurriness in the other.
How does that work?
Okay, think of a sound wave, a song.
All right, let's use audio.
If you want to know the exact millisecond a drum hits, I mean perfect timing, you have to look at a very sharp, very short spike in the wave.
A sharp impact.
Yeah.
Snap. Got it.
Right. But because it's so short, it doesn't really have a wavelength. It doesn't have a clear pitch.
Uh-huh.
So you know when it happened, but you lose all the information about what the note was.
Okay. And the reverse.
If you want a pure, perfect tone, a single clear frequency, that wave needs time to oscillate. It has to be long and spread out. So you know the pitch perfectly,
Mm-hmm.
but because it's spread out over time, you can no longer say exactly when the note happened.
So you physically cannot have both. It's not that you're bad at listening. The information just doesn't exist together.
Nature forces you to choose what you want to know. It has a resolution limit.
This is actually weirdly validating for any control freaks listening or, the optimizers.
How so?
Well, if you're the kind of person who's trying to optimize everything to 100% certainty before you make a decision, you're literally fighting physics. You're trying to know the position and the momentum at the same time.
It's a training arc,
Yeah.
really. You have to learn to become fluent in uncertainty. You have to accept that ambiguity isn't a bug in the system. It's a feature.
Fluent in uncertainty. I'm stealing that. Okay, so moving from uncertainty to connections, we have to talk about the one Einstein hated. Entanglement.
Spooky action at a distance.
He really, really hated it.
He thought it broke the universe.
So define it for us. What's actually happening when two things are entangled?
Entanglement happens when two particles interact in a certain way and become linked. They share a single quantum existence. Even if you separate them by billions of miles, they are still just parts of the same mathematical object.
So if I measure one of them, I instantly know the state of the other one.
Instantly. No time lag.
So, and I have to ask this because every sci-fi movie abuses this. Can I use this to send a text message faster than light? Can I take one particle to Mars and instant message lol back to Earth?
Unfortunately, no. You cannot transmit data faster than light. That rule still holds. Nature always covers its tracks.
So what's it good for? Why does it matter so much?
It's all about correlation. Okay, imagine you have two mystery boxes. You know for a fact one has a red ball and one has a blue ball, but they're sealed.
Got it. I take one box, you take the other, and I don't know, you fly to the moon.
I open my box on the moon. I see a red ball. Instantly, what do you know?
I know my box has the blue ball.
But faster than the speed of light.
Mm-hmm.
You know the content of your box. That's just classical correlation.
Right. Because the balls were red and blue the whole time. We just didn't know which was which.
Exactly. That's the classical world.
Yeah.
But in quantum entanglement, the balls do not have a color until the first box is opened.
Wait, so they're blank?
They are undefined. They are both in a superposition of red and blue, but they're undefined together. The relationship is defined. We are opposite colors, but the individual parts are not.
That's wild. It's a relationship-first reality.
That is a beautiful way to put it. The connection is more fundamental than the particles themselves. The us exists before the me.
And this isn't just some weird philosophy. This is the mechanism behind quantum computers, right?
It is. This is it. Because you can link particles in these complex states,
Yeah.
you can process information in ways a normal computer physically can't even dream of. Instead of ones and zeros, you have these vast interconnected probabilities.
Okay, that is another huge topic. We teased many worlds, now we're teasing quantum computers. We are going to have to make a choice soon about where we take this next.
Both are deep, deep rabbit holes.
Hold that thought. Before we wrap up the science, I have one really nagging question. We've talked about waves and probability clouds, things being in two places at once. If all this is true, why doesn't my chair disappear? Why isn't my car in a superposition of parked and stolen?
Ah, the question of why does the big world look so normal? The answer is one word: decoherence.
Decoherence.
So we said earlier that measurement is an interaction. Well, in the real world, the macro world, everything is interacting with everything all the time, constantly.
Like air molecules, light, heat.
Radio waves, everything. Your chair is being bombarded by photons from the lamp, air molecules are hitting it, vibrations from the floor. The environment is constantly measuring your chair.
So the universe is basically spamming the refresh button on my chair a trillion times a second.
Yes, that's a great way to put it. Superpositions are incredibly delicate. They get destroyed or decohered by the noise of the environment.
The analogy in the notes was the stadium whisper.
Right? Imagine trying to maintain a perfect, delicate whisper in a huge stadium during a rock concert. The laws of physics allow you to whisper, sure, but the environment is just going to wash it out immediately.
So the classical reality that we live in, this solid, predictable world,
Is just quantum reality after the noise has scrambled the interference pattern. It's the average of all the chaos.
that is weirdly comforting. The stability we feel is just chaos that's been averaged out.
Precisely.
Okay, let's bring this all home. We promised a mental operating system upgrade. So what does this all mean for the person listening right now? What are the practical takeaways?
I think there are three core principles you can take from this.
Hit us with them. Principle 1.
Stop demanding certainty. Reality isn't always definite until there's an interaction. Sometimes things are genuinely in a state of probability, and if you try to force a definite answer too early, you might actually be fighting the nature of the system.
Okay, visualize the probability cloud. Got it. Principle 2.
Questions have costs. Measurement changes outcomes.
What you track, you shape.
Exactly.
Yeah.
In business, in relationships, whatever. If you start measuring a new metric, the behavior of that thing will change. Your attention is an interaction. You are part of the system you're observing.
And principle 3.
Relationships are fundamental. Entanglement teaches us that sometimes the connection between things is more real than the things themselves. You can't always understand the parts in isolation. You have to look at the correlation.
This is why high performers are so drawn to this stuff. It's not about memorizing the periodic table. It's about training your brain to stay clean and functional under uncertainty.
It is the ultimate mental flexibility.
Okay, we have covered a ton of ground.
Good.
I want to lock this in with a super rapid-fire recap. I'll run through the key points. You just check my work.
Let's do it.
All right, here I go. 1, particles aren't marbles. They're probability waves.
Yep.
2, they can exist in superposition multiple states at once.
Correct.
3, the double slit experiment proves this with interference patterns.
The smoking gun.
4, measurement is not passive. It's an interaction that forces a result.
Crucial.
5, uncertainty is built in. You trade precision in one area for fuzziness in another.
A universal trade-off.
6, entanglement links the systems so their relationship is stronger than their individual identity. 7, the wave function is the menu. Measurement is the meal.
Love that one.
And 8, the world looks normal because of decoherence. The environmental noise just wipes out the quantum weirdness.
The stadium rock concert.
How was that?
Perfect. If you can explain those 8 lines to a friend, you understand the foundation better than 99% of people.
And that brings us to the end, but not really the end, because we have a choice to make.
We do.
Quantum mechanics doesn't say reality is meaningless. It says reality is just deeper than common sense. But we teased 2 massive topics that we just could not fit into this deep dive.
And we can't do both next time.
So we need you to vote.
Option A is part 2, quantum computers. How we actually harness all this probability to build machines that can solve impossible problems. It's the engineering path.
Or option B, part 2, many worlds. This is the philosophical deep end. We're talking parallel universes, branching realities, and where all those other possibilities actually go when the wave function collapses.
2 very different directions.
Yeah.
Engineering or philosophy.
So tell us in the comments, computers or many worlds, the choice is yours. Go ahead and collapse the wave function. And remember, you're not behind, you're just upgrading your operating system.